receiver near my phone. Yeah. Okay. So what I'm going to talk about is this trip I took to see the aurora borealis in Iceland. And most of what I have is just pictures. So I only have 2 slides with words on them. This first one is just a little bit of background. It was basically the end of September and early October that I went on this trip, and it was a sky and telescope tour. And some of my friends had been to Iceland, and it sounded like a really nice place to go. And I always wanted to see the aurora too. And I was looking in the magazine, and there was this tour with both, and it was like, okay. And I signed up like on the spot practically. So except for 2 nights in Reykjavik, the tour was basically totally in dark places. All the hotels were in very remote places, and it was very dark so that we could see the aurora better. And I do have probably half the presentations is the aurora pictures, but I do have some slides of Iceland too. So just a little bit about aurora. Probably a lot of people know this, but it really has to do with the sun. And it's the result of energized particles that are from the sun that are interact with the Earth's magnetic sphere, which comes from the solar wind. I'm having a hard time seeing it on my slide here. Lose something. Okay. So it's these energized particles interacting with the magnetic field and the atmosphere that cause the colors, basically, of the light that's emitted. And because it's all dependent on the sun, there's no guarantee you will see it, because all this stuff could be pointing entirely the wrong way and not even come towards the Earth. And so I went on this trip. I knew I would see Iceland, but I had no idea if I would see the aurora. And it turns out that there's a better chance of seeing them around the equinoxes. So when we left, the fall equinox had just happened. And I don't know if anybody's been paying attention recently, but last week was also the spring equinox, and there's been some pretty big magnetic storms just in the last week or so. So it turned out, though, that we actually saw them 3 nights, which from talking to other people who had been on the tour, the same tour in previous years, they'd seen them only twice. So we were really lucky. So this was the first night we were there, it rained. In fact, the weather was kind of so-so. It was, I don't think it got into the 50s. It was in the 40s and raining a lot. So the first night it rained, but the next 3 nights after that one night were totally clear, and we saw the aurora every night. And so for me, this was the first time I'd seen this. So I was like, I felt almost like a solar eclipse, if you've ever had that experience. Like, oh my God, I'm actually seeing it. And I was taking pictures and, didn't know if there would be any more, maybe this was it. And if you notice this picture, this is pointing towards the north. And it's not really that high. It's kind of nice picture, but it's not really that high in the sky. Well, little did I know, the following night was a pretty big magnetic storm, and this happened. So that previous picture, like I said, it was just in the northern horizon, low to the horizon. It was everywhere this night. So this is towards the north, and that's towards the south. And this picture is a little different than the other one. It kind of gives you a better idea of just how big they are. This was the hotel we stayed at, and the auroras were a thing with them. They even had a wake-up call service that they would call you, but that I thought I was going to be woken up in the middle of the night, but it turned out at 10 o'clock they were there. So I wasn't even asleep yet when this happened. And go back here a little bit. Oops. I'll get to that one next. So there's some kind of classic things of aurora pictures that you see here. One is, if you've ever seen them, they actually are sort of alive, is the word that comes to mind with me. They're moving all the time. And so to take a picture like this and have enough exposure, you need to take a long exposure. So not really long, but these are 4-second exposures. And because the aurora is literally moving all the time, turns out to be kind of blurry, which you kind of see here. So that often is what you see when you see an aurora picture. It's a little kind of blurry. When you see it with your eye, it's more gray, which kind of like a lot of what we see at night. Instead of all these colors, you see more gray. And but on this particular night, it was so bright that in these kind of bigger or brighter areas here, you actually could see little tinges of green. So there actually was color visible. And some people are saying they can get even brighter than this, and it becomes even, the brighter it gets, the more obvious to see the color. Yeah. No, I mean, everything you see here, rather than being green like in this picture. Oh, this is the here, you mean? This. Yeah. Oh, like this. Yeah, it was more like that color. Yeah, it looked more, you could see all this detail, but it was just gray instead of green. Yeah. And then this is the one that was probably the highlight of the entire night. And this was directly overhead. It was literally kind of like an explosion almost. And I mean, it was unbelievable. And so while this was all happening, I was looking up, but I also had my camera and I had this little shutter thing in my hand. So I was trying to take pictures as fast as I could. And the idea was I was going to try to hook these all together, sort of, or just stitch them together kind of into a movie. So I've got a couple of those. So remember, the movies are 4-second pictures that are just stitched together. So it's kind of herky-jerky because it's not smooth, but at least it gives you some idea kind of the movement. And so, oops, that was quick. Oh, it's not showing. We got to do something different here.
It looks like a raptor.
Yeah. I shared my, you know how it goes with Zoom. You share your thing and then it's not the thing that you're. Let's see here. Yeah, that's what I'm doing.
The colors to be green?
No, that's just what it does when you take a picture. The pictures, their exposures are long enough that the color, which is there, just, okay, now it's working. Okay, yeah. So this is a 16 of those 4-second exposures just sort of stitched together. So the real elapsed time of this is about 2 minutes. So this is actually faster than it was in what you saw. Yeah, these are all 18 millimeter. So what you're seeing is about, well, you can kind of get some idea from the cars down here how big this is. Oops. But it's about a 90-degree field of view. And then this next video is basically this thing. I mean, this was by far the best of what happened that night. I mean, to me, it just looked like an explosion. And the thing that was kind of amazing to me about that picture was, even though there's blurriness, there's still a lot of detail. So it was like super bright and kind of moving, but sort of stationary at the same time. So it allowed you to get some detail or sharpness. This was straight up, literally straight up. Yep. Well, like I said earlier, there was north, south, and I mean, it was everywhere. It was almost like, where do I take a picture? And I honestly, I'm not, I guess I was just kind of looking all over the place. And then I saw this and immediately moved my camera because it was so bright. And I guess I was lucky to get so much of it. But here you can even see there's a little red in there too. Yeah.
Tripod mounted camera.
Yeah. Yep. Yeah, they're not moving at all. They don't move at all. It's totally Yeah, I had this, like I said, kind of a push button shutter release that was on a cable. So I was sort of, other than the cable, I wasn't touching the camera at all. So it allowed it to be pretty stable.
Sound associated?
No, no, other than the people yelling and screaming. So that was what I had as far as the aurora. I just had I don't know, maybe some people have been there, but Iceland, it turns out, is right where some of the tectonic plates are pulling apart. So there's all this volcanic activity. And in fact, I think the reason Iceland is there is because of all that. It's kind of like the reason the Hawaiian Islands are there. It's the volcanoes. So in April of last year, so about a year ago, but about 6 months when we were there was a lava flow. And this is it 6 months after it happened. And it was solid, but you can still see it's hot and steaming in the background. And I don't think I would have wanted to walk out in the middle of that. So Iceland, because they have all this geothermal activity, their total electrical system comes from the geothermal, and which is great from an environmental perspective. So they extract the energy from the steam, and they're left with all the hot water. And so they end up with stuff like this, these lagoons with the hot water. And this one is called the Blue Lagoon, which is kind of famous, sort of one of the touristy trap ones. But this was the first thing we went to, and it was one of my favorite things. I really enjoyed it. And this is a little bar here. And one of the things that amazed me is you could get a beer, and they gave you a beer in a glass in a pool, which, where does that happen? Except in Iceland, I guess. So this is an example that you can actually see sort of results of the tectonic plates. This is actually the edge of one of the plates, basically, what you're seeing here. Then this big valley, and I guess the other side is somewhere over here to the right, but this is the western edge. And this is a national park. Very, very pretty. I mean, this is the same day of one of the auroras, so you can see the weather was actually pretty good on some of the days. Of course, geothermal, you get geysers too. And this is actually in the town of Geyser, and that is actually where the English word geyser came from. It's a Icelandic word, actually, or derived from that. Tons of waterfalls. In fact, it sort of got to the point, it's like another damn waterfall again. But we did go to at least four waterfalls that I could think of, but they were all actually really beautiful waterfalls. This was probably the biggest one. This I thought was, it doesn't really come across in the picture, but I thought it was the most beautiful thing that we went to. There's actually a glacier here in the background, and it's melting, and there's this big pool at the bottom or base of the glacier, and all the pieces of ice from the glacier break off into these sort of miniature icebergs. And the color, this blue color, was just beautiful to see. And this is the last picture.
I had a question about the
Yeah.
waterfalls. Are the waterfalls hot water too? Or
No,
just-
they're cold. Yeah. No, they're not related to geothermal at all. Yeah.
It's just cold outside.
Yeah. It's probably melting ice or rain, one of those two things. So, yeah. So this is Reykjavik. The country of Iceland has less than 400,000 people. So the grand total, there's probably as many tourists there as people, but and then Reykjavik itself has more than half of the population. So it's not a big town, but it's a really nice town, really beautiful, clean town. This spire you see here in the background is kind of the iconic thing of the town. It's a church, and unlike a lot of the European churches, it's not hundreds of years old. It actually was started to be built in the 1940s, and it was finished in the 1980s. So it's, less than 100 years old. But it was just a really nice trip, and I really enjoyed it, and I really enjoyed Iceland. And I just felt super lucky to see the aurora. So that's what I had. Any questions?
So when you going back?
It's kind of like with me, there's so many places to see in the world. Once is enough for everything.
Well, Dan, as beautiful as all your photos are, I'm sure they just don't really do justice to the real thing.
Yeah, I mean, the thing that's missing is the movement. I mean, I didn't really know what to expect in terms of what it really looks like to see them. And like I said about them being alive, it's really what it looks like. They're moving continuously. It's not this slow movement that you can't see. You can see it moving continuously. It's pretty amazing. Yeah.
Three things, comment.
Yeah.
Iceland recently made the top 5 list of the happiest places in the world.
I believe it.
Do you know what causes that kind of visual curtain effect?
Oh, you mean on the aurora? No, I don't. I'm sure obviously it has to do some obviously with the way it interacts with the magnetic fields, but I don't know.
And they all seem to end at a certain point. It must be the bottom of the ionosphere.
Yeah.
Okay.
I mean, it's all has to do with where the particles are in the magnetic fields. So
Looks like they're coming down.
yeah. I don't know. In the back. Yeah.
Hang on.
Beautiful presentation. Thanks.
Thanks.
A quick question. So, obviously going with S&T must have been wonderful, but it's pretty, I think the ones I've seen at least are pretty pricey.
They
Can
are.
you just talk about that experience and what you thought about the value of
I mean, it is pretty expensive, and I went by myself, which adds even more on top of it. But I was amazed how nice everything was. It was, I mean, I've been on a lot of tours, and the hotels we were in were like really top class hotels. Every single meal was really nice. The dinners especially were like, I felt like we were going to some of the best restaurants in town. It was all really good, and they kind of pampered us too. It wasn't a big walking tour. There was a bus. It kind of took you everywhere, and you didn't really have to walk very far to everything. Not everybody likes that kind of stuff, but if you're more into just kind of not having to work too hard, it was pretty good that way. Yeah.
Dan?
I don't know where's that coming
I
from.
think that's
Oh.
online.
Hi, this is Pete on Zoom. Can I be heard?
Yeah, we can hear you.
Question. How bright in person was the aurora relative to what we're seeing now, like in percent? Is it equal brightness or 30% as bright in person?
I would say this thing here, it's hard to say going back, but I would say it wasn't quite this bright, but it was close. It was pretty obvious. And of course, we were, like I mentioned before, we were in a dark place. I think this one in particular, if you were in the city, you still would see it. It wouldn't have been as vivid, but I think this one you would have seen it in the city. The third day, which I didn't even talk about because it was sort of the worst of all. I mean, it was more just like this glow. The first 2 days you could obviously see, there's definition there and the curtains and, this sort of eagle shape and all that. The last day was more just like this vague glow. And in that case, you never would have saw that in the city. But yeah, they can be, I mean, it was, when I walked out the second night with this big storm, I think my jaw literally dropped.
Wow.
I couldn't believe how bright it was. Super bright. Yeah, it's not
Amazing images.
And seen the Magellanic Clouds. I don't know how many people have seen that. They're kind of sort of hard to see. This is totally different, totally obvious.
You also mentioned that the green isn't as pronounced.
No, you don't see it like this, but you might see it, like I said, kind of, this one here, these bright spots, you would see tinges of green. You
Okay.
can see the color with your eyes at night, which is unusual,
Yeah.
at least from what I've seen.
Amazing images. Thank you.
So does anybody here at Lindsay have any questions? Any more?
I don't know if
No?
there's any chat
Okay,
questions I
Okay, well,
saw.
there's actually a couple. Oh, sure. Oh,
Okay, there's a question about the brightness.
Yep.
I guess that was it.
So Dan, do you know what molecules or atoms cause the different colors, red
I
and
think,
green?
I think oxygen is the green. I'm not sure what the red is.
The oxygen also
Yeah.
is the red too,
Okay.
but that's usually at a different altitude. And what you're seeing there
Yeah.
is you're seeing
Yeah.
over a whole range of altitude. But that's above, I think, what is it? I think 150 kilometers or something like that on up. So at least that's what I was reading at least recently. Did you see anything on chat?
I would, that last question about the
Okay.
brightness, that was it.
Okay, all right.
Yeah.
Well, thank you, Dirk.
Yep.
So, all right, now we're recording and everything. I can then introduce tonight's talk, which is Following Galaxies from Birth to Death with the Largest Time Machines. Pleased to introduce Dr. Andreas Faisst to our meeting tonight. I hope I did that correctly, Doctor.
Perfect.
Dr. Faisst was born in Zurich, Switzerland, and is an astronomer at the Infrared Processing Analysis Center, IPAC, at the California Institute of Technology in Pasadena. He uses the largest telescopes on the ground and in space to study the formation and evolution of the first galaxies in the early universe. He pursued his undergraduate and graduate studies at the Swiss Federal Institute of Technology in Zurich, ETH Zurich. In 2015, he obtained the Doctor of Science in Astrophysics from ETH Zurich. A prestigious fellowship by the Swiss National Science Foundation allowed him to continue his research, as a postdoctoral researcher at Caltech. Since 2019, he has been on the research faculty at Caltech. He has been active in outreach, giving numerous talks and tours, and is a co-leader of the Caltech Astronomy Outreach Team. In addition to his academic career, Andreas is a semi-professional web designer, a former pilot of small airplanes, a pianist, and a passionate volleyball player, mountain biker, and swimmer, as well as billiards player on the national competition level in Switzerland. Now,
Wow.
as if he didn't have enough things to do, please welcome Dr. Faisst.
Oh, thank you. Okay, let me share. Okay. How does it look?
That looks fine.
Good.
Cool. Okay. Yeah, so thank you for the very nice introduction. I was trying to come up, but then it unfortunately didn't work out with the time. But I'm glad to be here remotely and tell you something about the first galaxies with the largest time machines, which is currently at JWST. Okay, so move some windows here. Okay, so you probably know this image. So that's the SMACS 0723 galaxy cluster, which was one of the first images that JWST sent back to Earth. And it's a very nice image because you see many different object sources on this image. And so the cool thing is that this is a gigantic, massive galaxy cluster. So you see the white galaxies here. These are all galaxies that are close by. And then you see this star here, which is a star in our Milky Way. And then you see this distorted red sources here everywhere. And these are background galaxies that are being distorted by the dark matter mass of this gigantic galaxy cluster. So these are background galaxies. And so if we look a bit closer, we can identify identify different types of galaxies. So we see those, well, very nice spiral galaxies. And then we see those galaxies that are kind of looking a bit boring, right? And then we see something between where we see very irregular galaxies, galaxies that are colliding. And the reddest points here, which I zoomed in on one of them, these are galaxies they're very tiny and they're very red. So these are actually very, very far away at the beginning of our universe. And so we found that basically there's a time evolution in how the galaxies change their structure over time. So the two galaxies you see here on the right-hand side, these are basically galaxies that we see today. So about 13.7 billion years after the universe was formed. And those funny-looking galaxies here in the middle, they formed about 3 billion years, 3 billion years after the Big Bang, or about 10 to 11 billion years in the past. And so the most tiny red things you can see here, they have been formed only 200 to 300 million years after the Big Bang. And so I will explain you that a bit more in detail later, but there's also something we call redshift, and that goes the other way. So redshift 0 is basically today's universe, right? And when you go to infinity, that's basically where the Big Bang happens. So redshift 15 corresponds to about 200 million years after the Big Bang. So what am I doing except, playing pool and flying planes and do this other stuff? So I'm trying to connect the dots, right? So I'm trying to see how the galaxies over time change, how the different galaxy populations change, and how those galaxies get enriched with metals and dust, and eventually how and when actually the galaxies die or stop forming stars. Okay, so this is the outline for the talk. I want to give you a brief introduction on galaxy formation and evolution, so what we know today. And then I want to introduce you to the James Webb Space Telescope and why we actually need it, why it's useful. And then the third part, I will show you some of the newest results from JWST that have been, basically published in the past couple of months. So you probably know that most of the universe we actually can't see. So there's dark energy that pushes the universe out, and that causes the expansion of the universe. And then we have dark matter, which is something else we don't see. And then we have baryons or ordinary matter, which is what we are out of. So, right, it's only 4% of the total matter density in the universe. So let's start with dark matter. So dark matter is basically the backbone of the universe, and it builds a web that we call the cosmic web. And dark matter is very easy to simulate with computers because dark matter is collisionless. So it's basically there is no physics, right? It's only gravity. And that's why we can, when we trace how the dark matter looks like in the universe, we can basically predict or constrain our cosmological parameters, for example, how the expansion of the universe or how the structure formation happens in the universe. So since it's so easy, I created my own little fully realistic dark matter simulation here in PowerPoint. So you see two dark matter halos. In those dark matter halos, there are galaxies. Because what the dark matter basically does, it collects the gas through gravity. It falls into the dark matter halo. It condenses, it compresses and forms stars. And that's how you form galaxies in the end. So what happens if two of those collide? Well, let's see. So they're getting closer. Even closer. Even closer. And now something interesting happens. So the gas, because the gas is not collisionless, so it actually collides the gas, the atoms and the molecules. So it stays in the center while the dark matter just passes through it. And same, by the way, with the galaxies, right? So the galaxies are so far apart, so they're basically collisionless. So they don't interact with each other; they just fly through and follow the dark matter. And that was very important to understand what dark matter is. And that has been measured actually. So the picture I'm showing you here is the bullet cluster, which you maybe know. So the dark matter was measured by weak lensing, which is basically how the dark matter distorts the shape of galaxies behind this big cluster of galaxies. What I showed you on the SMACS image in the beginning. And the gas here is in red, and it's basically X-ray emission. And that has been shocked when it was compressed, and that's why it glows. And so that's basically what dark matter is. It's collisionless, while gas collides and forms stars and gets compressed and forms stars. And so now you can simulate basically a big chunk of the universe with dark matter. And so that's the dark matter structure about 200 million years after the Big Bang, or redshift 15. If you let time grow, you see here 1 billion years, redshift 6, and 4.7 billion years, redshift 1.5, and today. And so you see how the dark matter collects and forms those knots of big, heavy dark matter accumulations. And this is where galaxies form. And so you see here, this is a overdensity of dark matter, and it's also an overdensity of galaxies. And gas is basically flowing in on those highways of dark matter, which we call filaments. And this is exactly what I showed you on this first JWST picture, right? So this is the white stuff that you see here. These are all galaxies that are belonging to this galaxy cluster that's in this big, massive halo of dark matter. And all the galaxies behind, the red ones here, and the ones that are distorted, they are behind this structure. So that's pretty cool. But as soon as we get to galaxies, it becomes a bit more complicated, right? So what properties can we actually track over time of galaxies? So there's first model structure. So like properties like size, compactness, how many spiral arms there are, is there a bar in the center? Then the mass of stars and dark matter in the galaxy or around the galaxy, the mass of gas and dust, the rate of star formation, so how many stars are being formed per year, and any chemical properties, which in astronomy, we basically just call metals. Right, so metals are basically whatever is heavier than helium and hydrogen. Very simply. And so we can simulate those galaxies also in a computer. It needs a bit more time, but we can do it. And this is what I'm showing you here. This is a simulation of a galaxy that is pretty old by now. And you see here, up here, the redshift, how it evolves over time. And now you can see something interesting. So you saw in the beginning, it was kind of irregular and turbulent. And now over time, so we now passed about 12 billion years almost. It's pretty quick. The galaxy starts to look more smooth. But you still see those explosions in the center. And this is whenever the galaxy forms a lot of stars, a so-called star burst. It builds up pressure and it basically shoots out gas into the never-ending universe. And so you can actually see how some of the smaller stuff falls on the galaxy and the galaxy starts to eat up all the smaller dwarf galaxies around it. There's a bigger one happening here. Oh, went past, but it's probably coming back. And now I see over time you build this nice spiral galaxies. That's basically what we think our Milky Way looks like today. So you basically evolve from this like turbulent thing into this nice spiral galaxy. And so these are nice simulations, but can we actually observe that? Well, I have to tell you a bit how we actually measure galaxy properties. So galaxies look different at different wavelengths. And that tells us, and so each wavelength tells us something about the properties. So we have basically two methods to measure the galaxies in different methods, wavelengths. So we have imaging, which is basically what you do with the camera, right? So you take a picture and you take the picture in different filters, right? And so as you've seen from the previous presentation of the auroras, they have different colors, right? They're green and they're a bit of red. And that tells you about different elements and what height they are being emitted. And so it's basically the same with what we do. We image the galaxy and we just look at the color. Is it more red? Is it more blue? Right? So that allows us to give like an approximate, properties of those galaxies. So the imaging is great because you can just take one image, right? The one behind me, and you get a lot of galaxies, right? And you can do it very deep. You can integrate very deep. Spectroscopy is a bit harder to get, so it uses more telescope time because you disperse the light into basically the wavelength, the rainbow spectrum. But you get a lot more of information out of galaxies. And that's just, again, an image to show you how the different wavelengths, how the galaxy looks in different wavelengths. So that's a Whirlpool galaxy. I believe it's M51, which you actually see right now. And when you look here in the UV, you see those clumps here. And these are active star-forming regions in the galaxy. The optical is basically what you would see with your eye, right? You see, this is a bit smoother. If you look in the infrared, you see all this dust in the galaxy. You see there's a dusty core, and then there's dust out here. The galaxy out here that's merging is actually not very dusty, right? It's more blue. And then when you look in the radio, you see all the coal gas. So this is actually where stars are being formed. And you can see here that most of the stars are being formed in those spiral arms of the galaxy. And so basically what we do, we look at the galaxy, we measure the light in different wavelengths. And so you see here wavelengths on the horizontal axis, brightness on the vertical axis. We have those different filters and we measure and we get some measurements. Okay, cool. Then we go to another galaxy, we measure, get more measurements. Great. What does this tell us? Well, we have to either compare this to models or we have to do spectroscopy. And this is how it looks when you do spectroscopy, right? So the lines are now very fine gridded in wavelengths, right? So from the dispersed light. And you can now make out some more properties, right? So you fill in the gaps basically, and you see there are some, emission lines here and some absorption lines. So dips in the spectrum and peaks in the spectrum. And so it turns out that absorption lines are produced by old stars, while emission lines are produced by regions of active star formation. So when you now compare those two, you can see that the blue galaxy here is actually forming stars, while the red galaxy here doesn't, right? And we call those passive and active galaxies. So star-forming galaxy is active, and the passive galaxy doesn't form any stars anymore. It's like a dead galaxy. And it actually looks red, right? Because you have more brightness here in the red part of the spectrum than in the blue part. And so there's another thing that's important. So these are galaxies that we look at, in the local universe. But now Edwin Hubble in 1929 measured something interesting. So what he did is he looked at galaxies, but at that point they called them nebulae, so like clouds, right? Because they didn't know at this time what those are. And he measured that for those galaxies that are farther away at greater distance, they are moving away from us much faster. And now that's basically the same as the Doppler shift, right? So when something is moving away from you quickly, the wavelengths get shifted red. And if something is approaching you, it's shifted blue. So we can modernize this diagram a little bit. And we can call the radial velocity or speed, we can call this redshift, z. And the distance, we can call this look back time, because the speed of light is constant. So which means when you have a galaxy that's far, far away, the light needs time to get to us, right? So as you know, the sun is 8 light minutes from us, right? The moon is about 1 second, right? These galaxies are now millions, billions light years away. So redshift equals distance or look back time. So yeah, by measuring the redshift, which I tell you later how to measure that actually, from that we know how far away the galaxy is and how far look back we look in time. Or if we turn it around, we can say what is the age of the universe at the time where we see those galaxies. And so this is why telescopes are time machines. So we can, with Hubble, we look back, about 12 billion years in time. And with the James Webb Space Telescope, we can look back even further, basically to 200 million years before or after the Big Bang, where the first stars are being formed. So we should see the first galaxies being formed with the JWST. And so we can, so with this trick, right, when we look at galaxies at different redshifts, we can follow the evolution of the galaxy population. And so what I show you here is, again, as a function of time, how those galaxies change, right? So you have the very high redshift galaxies, they are super tiny, red. When you go back forward in time, they become kind of irregular, and eventually they become spiral galaxies. So exactly what we saw in the simulation before. So they did a great job in simulating galaxies. And so what we measured actually is that also the stars that are formed in galaxies change over time. So in the beginning, galaxies formed very little stars. So around here, 13 billion years ago. And then about in 2 to 3 billion years, they reached a peak where they formed a lot of stars. So it's like they're the best part of their lives. They're forming stars like crazy. And then later, in the next 10 billion years to today, you see that this number of formed stars per volume is going down. And so, well, why is that? Well, because galaxies start to shut down their star formation by some processes, right? So they basically die. Another thing we measured is that the metal content is evolving over time. So what you see here is on the horizontal axis is the mass of galaxies. So this is 1 billion solar masses, so 1 billion suns to 100 billion suns. So these are very, very massive galaxies. Our Milky Way is around 11 or 10 to 100 billion solar masses. So, and what you see on the vertical axis is the oxygen abundance. So how much oxygen you have, and that's basically our metallicity tracer, right? It's a heavy element for us, oxygen. And you can see here that over time, the oxygen abundance goes up, right? So galaxies, they build up their metal content. You also see that more massive galaxies are more metal rich, by the way, and low mass galaxies are less metal rich. So as I said, so the higher we go in redshift, the farther back we can look in time. But there's a problem, because obviously, as the name says, if they are redshifted, the spectrum is being shifted towards the red. So what we need to look at those galaxies in the infrared. And I'm trying to illustrate this here. So this is, again, the spectra we saw before. And now, what happens if you are at the redshift of 5? well, you shift your spectrum by a factor of 1 + 5, so 6. So whatever was here before is now shifted into the red. And that's a problem, right? Because, well, most of the observatories we had previous to JWST were operating here in the optical light, maybe up to 1 micrometer. But to actually see those redshifted galaxies and to measure their properties, we have to go into the infrared. And that's what JWST was designed for. So the infrared is important, one, to study the cold dust and gas in galaxies, but also to actually be able to see galaxies at great distances, at high redshifts, so the earliest galaxies. And so that this is kind of a cartoon of how much light is being transmitted through the atmosphere. Well, in this case, how much light is being blocked, right? And so you see here in the UV, basically 100% is blocked. So you need to go into space to see X-ray and gamma rays and ultraviolet light. And then by definition, the visible light here has a very low opacity. So that's why we see, right, visible light, because it comes through our atmosphere. Now when you go to the infrared, there are some places where you can see infrared light, right? There are some dips here. But the problem is that infrared is heat. And so because everything that's warm is emitting infrared, like those cute animals here, and we have to go to space where we don't have those cute animals anymore. And basically to be blocked out of the sun, right, to actually see infrared light. And so there are observatories we do have in the infrared. One of them is Herschel, it's one here, was operating from 2009 to 2013. And then the Spitzer Space Telescope, which was operating from 2003 to 2020. And so especially Spitzer saw a lot of those high redshift galaxies, those little red dots. But you see the resolution of this image is not that great. And then there's also the Hubble Space Telescope, which goes up to 1.6 micrometers. It has a very high sensitivity. And you can see here, a lot of those high redshift galaxies have been found. So each of those red dots on this image is a galaxy that's above redshift 6. But the problem is it goes only up to 1.6 micrometers. So we cannot go higher in redshift. So to see even more distant galaxies, and you also have better spatial resolution, because I showed you before, those galaxies are pretty tiny. And to get also spectroscopy, we need larger telescopes. And this is basically what JWST does, right? So JWST in a nutshell, the mirror of JWST is actually coated with gold because it reflects infrared light, right? Because it's optimized for the infrared. So the total amount of gold is about the size of a golf ball. And I looked it up today. So the current value of about 0.12 ounces of gold is $230. So it's not worth to try to scrape it off. It's too risky. And now it's in space anyway. So, but the mirror is actually very big. So it's 6.5 meters, so 21 feet. And as you know, from like optical telescopes, the bigger the opening or the mirror is, the more light collection area there is, right? So you can see fainter galaxies. And what's really cool is the telescope is passively cooled through a sun shield. So I showed you before that basically infrared heat is infrared light. So you want to shield the telescope from any warm stuff that's there. And so the JWST is passively cooled. So it has these layers of, it looks like aluminum that basically reflect the heat in steps such that you have a hot side and a cold side. And the temperature gradient is just crazy, right? It's 185 Fahrenheit on the hot side, almost minus 400 Fahrenheit on the cool side. And you see all the communication, the computer and everything else, it's like on the hot side, right? While behind this sun shield is the instrument and the mirror. So as long as the instruments work, JWST is basically operating because it's not depending on any coolant, like the Spitzer Space Telescope, for example, that ran out of liquid helium, and then it cannot observe anymore in the infrared. The telescope is at the Lagrange point, which is about 1 million miles from Earth, around here. That gives it good visibility. It's very quiet out there, but the downside is that we cannot repair it. So not like Hubble, where we can just fly up and repair it. That doesn't work. But luckily it works. And so this is just, that was me. I think it was 2018. I was very young, with the JWST in the background, where it was, I think, close to LA, and waiting to be launched into space. And this is just, again, to comparison between Hubble, Spitzer, and JWST, which is just gigantic. So it's the largest telescope ever put in space. Well, and this is what you get, right? So on the left-hand side, this is what Spitzer imaged at 8.6 micrometers. And on the right-hand side is what we get from JWST, the same wavelength. Yeah, and you see yourself, it's quite a difference, right? In terms of resolution and sensitivity. And that's again, the SMACS cluster I showed you that obviously also has been imaged by Hubble. And just, to compare with the difference, this is JWST, and this is Hubble. You notice, I don't know if you can see it on your screen, but there is like this fuzzy stuff around in this cluster. And this is called intra-cluster light. And I will have, at the end, I have a couple of slides on that. It's actually pretty cool what's going on in there. Yeah, and then obviously spectroscopy, right? I mean, in the infrared. So we see all those emission lines of this galaxy at redshift 8.5, which we don't even have models for that. So we're actually calibrating our models now on those galaxies, of how those emission line ratios look like and how they match to the star formation rate and the structure of this galaxy. Okay, so in the last part, I want to show you some cool results from JWST and what we learned so far in the couple of months it's actually flying. So we broke a lot of redshift records. So this image shows you the near spec instrument field of view, so those 4 quadrants. And so of almost every galaxy there, we can get a spectrum. And you see 4 of them here highlighted. And these are the highest redshift galaxies that we have ever observed and confirmed. And you see here, they're at the redshift about 12, 13, 11, almost 14. And we don't only confirm them, we can also measure their physical properties, right? So this is, again, imaging. So you see here, this is the F090W, so white filter, which is at 0.9 micrometers, up to F444W, which is at 4.44 micrometers. So red to blue. You see in the top row, the image, right? And you see that the galaxy is not here in F90, F115, F150, and then suddenly in F200 it appears. 277, it's bright, and then it kind of stays at the same brightness. And so we can measure the brightness of each of those filters, and this basically what I'm showing here on the bottom. And so you see when in those first 3 bands, there is no detection of the galaxy, right? And what we measure here is this so-called Lyman limit. This is where neutral hydrogen in and around the galaxy is absorbing the galaxy light, the blue galaxy light. And so basically how strong this drop is tells you how much neutral hydrogen there is around this galaxy. So that's pretty cool. But we can go one step further. So this is now a spectrum. So you see it's much more detailed. You again see here the Lyman break where the red line is. You see here a couple of like absorption features, a couple of emission lines. And from that, we can actually measure how much metal does this galaxy has. And well, as expected, as you might think, it has a very low metallicity. So this is a very pristine, young, immature galaxy. And this is how it looks like. It's a tiny little blob. So I get excited about this. Maybe you don't. It's too small. And this is the comparison to the Milky Way, right? Milky Way is much bigger. So this is a tiny little thing. So redshift 12.63 is about 300 million years after Big Bang. So now we're kind of at the limit, right? When are stars being formed? I mean, there's not much time anymore. I mean, 300 million years is not that long, right? And you have to form stars and mass of these galaxies. So that's interesting, constrains our model of how galaxies are being formed. So yeah, chemical properties, what do we learn, right? So we would expect that in those very tiny little balls of gas, there's a very strong radiation when stars are being formed. It's basically a lot of pressure, and they are very metal poor. So we can see if this is the correct. So this is now a little bit complicated here, but basically what you can focus on is the vertical axis, which shows you the ratio of doubly ionized oxygen to singly ionized oxygen. So to double ionize oxygen, you need a lot of ionizing radiation in those galaxies. And well, true enough, you see here, all those high redshift galaxies that we measure with JWST are very high up here on this vertical axis, much higher than today's galaxies that are, yeah, they don't really have a high ionization field. So they don't have much star formation going on anymore. And what about metals? Well, this is the same diagram, but now on the horizontal axis, I show the ratio, abundance ratio of neon to oxygen. And that correlates very well with the metal content of galaxies. And again, high redshift galaxies are up here. But what I find kind of interesting is those red crosses. It's a bit the wrong color, but they're actually called blueberries. And blueberries are galaxies in the local universe that have crazy strong, crazy high star formation rates. So they form a lot of stars per year. And look, they are at the same region as those high redshift galaxies. So this tells us that the physics in those early galaxies is very similar to what we observe in the universe today, in the most extreme objects that we see today, those blueberries. Yeah, these are very metal poor galaxies in the local universe. So that's kind of a link, you know, to the very early times, 100 million years after the Big Bang to today, 13.7 billion years after the Big Bang. So what about the structural evolution? Well, some of us have looked at the image and then classified galaxies in either this galaxy that you see on the top row, so it's a bit disky, elongated, and spheroids, which are likely galaxies that are not forming stars anymore. So they look very compact and a bit reddish. And so we counted them over time, and we have found many more disk galaxies, or I should say we have found disk galaxies at the very early times that we haven't seen with Hubble. That's mainly because the sensitivity of Hubble compared to JWST is much worse. So we didn't detect those galaxies. And what this tells us is that even 500 million to 2 billion years after the Big Bang, we already have those, what you could call nice spiral galaxies that we see today. So some of those galaxies, they look like today almost, maybe a bit smaller, but similar structure. So that was interesting. And then, so this diagram, you maybe remember, it's the stars formed per volume as a function of time or redshift. I told you here that after this peak of stars formed, it drops. And that means that galaxies are stop forming stars. And so, well, a dead galaxy forms 0 stars per year. Our Milky Way is not that active anymore. It forms about 1 to 2 stars per year. And galaxies here, about 10 billion years ago, they form hundreds of stars per year. So 2 orders of magnitude more. So the question is, why do they stop their star formation? Right? What happened to them? There are multiple ways to stop star formation, and one of them is probably the most exciting one, is to let them collide. And so that's an image of the antenna galaxies in the local universe. And probably you can probably see them in optical telescopes. So what happened here is 2 galaxies collide. And what that means is that the gas in between them is being compressed. And that means that stars are being formed more efficiently when you compress the gas. And that's what we call a starburst. But the problem is, it's like when you're driving a car and you accelerate a lot over a long time, you eventually run out of gas. And that's what happened here too. So they form a lot of stars, but they use up the gas extremely quickly. And if you don't have cold gas anymore, you cannot form stars anymore, unless you have more gas flowing onto the galaxy. But if that doesn't happen, then you stop forming stars. So basically, you have 2 galaxies, you smash them together, they collide, have a starburst, their disk structure is destroyed, they form this dead, like boring spheroid galaxy, elliptical galaxy without structure, and they stop their star formation. And so now the question obviously is when does this happen, right? So we have seen quiescent galaxies up to redshift 2 or 3 maybe, but we don't know what are the progenitors of them. So when do they stop forming stars? And again, if you look at those spectra, as I said before, we can identify passive galaxies if they don't have emission lines, and mostly absorption lines that you see here, those tips. And to our big surprise, we found the passive galaxies that lived 500 million years after the Big Bang. So if you go back to this diagram here, that's like here in the beginning, right? While most of them start to appear after 10 billion years. So what's going on, right? I mean, we haven't solved this issue yet. And so that's the galaxy, right? So you see here again, the Lyman limit, you see absorption lines, and you see this is called the Balmer break here. You see more absorption lines, but you don't see any emission lines where they should be. They should be here and here and here. So that galaxy really is shut down star formation at 500 million years after it's being formed or less. And so we think what happened is that galaxies, they are on and off, right? So they form a lot of stars, then they're passive, and then they have more gas flowing into them that again starts up star formation. They are star forming again, and then they collide again. They remove gas, consume gas, and become passive again. And so there's kind of an up and down in the star formation rate of those galaxies at these early times. And then eventually, they don't have gas flowing into them anymore, so they just die and become passive for good. And obviously, so more data is always better. And so I'm on a program that's it's the largest JWST imaging program, and it's being done on the cosmos field. And you see here, it's a 2 square degree field, so it's the moon for comparison. It's much bigger than any other fields that have been observed with Hubble, and it's very well studied. And so this Cosmos Webb from JWST Cosmos program has been approved in the center of this Cosmos field. And since January, we have 4% of the data, and this is what it looks like. So this is the first batch of the data that we got. And I see here very nice, very different galaxies, spheroids, spiral galaxies, some mergers, some weird looking galaxies. So eventually, this is now ongoing, this program. We can find the most massive galaxies in the early universe. We can see how the structure of galaxies looks like, the large scale structure, right? So that this dark matter web that I showed you in the beginning, how that looks like. And we can also combine with radio telescopes like the Atacama Large Submillimeter Array, or ALMA, to probe in radio wavelengths, to probe the dust and gas of those galaxies. And that's a program that I'm leading. So if we focus on this epoch where galaxies are starting to form their stars, and we have about 100 galaxies imaged with ALMA. So we know how much gas they have, how much dust they have, and so we can connect the dots. And basically, what JWST gives us is, well, if you compare here Spitzer JWST, big difference. We can actually see where the gas here in red contours is relative to the rest of the galaxies or the stars. And in this case, you see that the gas is actually not coming from the stars. It's actually coming from between those three galaxies. So that might hint that these three galaxies are colliding and the gas in between is being compressed and starts forming stars. And to end it, I want to go back to the beginning, to this image, to the most massive structures, right? Those massive galaxy clusters. And let's focus at the same time on the smallest structures in our universe. And so it's trying to increase the contrast here. And what you see is this diffuse light here, and that's what we call the intracluster light. And that's gas and stars and star clusters that are in this gigantic, massive galaxy cluster. So that it's like free-floating star clusters everywhere in between those galaxies. And that's pretty interesting. So if I zoom in here, you see here like those tiny little dots. So this is not like, these are not artifacts. These are actually star clusters. And these are not star clusters like the Hercules cluster in our Milky Way. These are star clusters in this, around these galaxies that are about 4.3 billion light years away. There are some brighter dots here that are probably very red stars from our Milky Way. This smudge here is probably a galaxy in the background, but you see all those dots here. These are star clusters. And that's very interesting. So that's also another thing JWST can do with its sensitivity and resolution. We can actually see those star clusters of the size of Hercules and 13 in this very far away galaxy. Okay, so that's already the end of the talk. To summarize some takeaway points, telescopes are like time machines, right? So the bigger the telescope, the more you can look into the past, currently up to 200 million years after the Big Bang, where galaxies should form stars. So if you go in further, then at some point you wouldn't expect galaxies to be seen anymore, unless our whole picture of the universe is wrong. And galaxies evolved significantly. They had a peak of star formation about 10 billion years in the past. They evolved from irregular systems to disk systems and eventually stopped their star formation and become these rather boring looking spheroids. And with JWST, hopefully I could convince you that we can do a lot of science on those, and it's a really exciting time. And we only had it for a little bit, so I can't imagine what's being seen in the next 5 years of JWST time. Okay, and that's the end of the talk, and I'm happy to take questions.
Hi. I got a couple of questions in the room here. Hang on just a second. Mash this. Oh, there you go.
Okay, so I have two questions. The first question is about dark matter. Since there's
Mhm.
5 times as much dark matter as regular matter, does it affect gravity in the solar system? Is there dark matter being sucked into black holes, things like that? And my second question is, you alluded to a little bit, but how much of a revolution in galactic evolution is it that the James Webb Space Telescope found galaxies that were much further evolved than we thought would be possible at that early time? So those are my two questions. Thank you.
Yeah, they're very good questions. So the first question about dark matter, so it doesn't affect much the small scales. So it the gravity of baryonic matter, so what we see is basically much more important at small scales, so solar system level, as dark matter. So it doesn't affect really the solar system and also not our galaxy itself. And the second question, I mean, this was that was a big surprise. So I showed you, I showed you a bit those images from the radio telescopes, right? And so from that, we can actually also measure some, we also have some statistics on the structure of the galaxies. And there were hints that galaxies might look more like, you know, more uniform and less irregular at high redshifts. But we couldn't confirm that. And then basically and then with JWST, we actually could see it. And that was a very, very big difference. And basically what we couldn't do before is, I mean, one, sensitivity, right? And two, also the red wavelengths. And so we basically missed all the structure of the stars, of the old stars, which are emitting light in the red wavelengths. And so we could only see the newly formed stars, which are basically at a very different location where the old stars are, right? And that's why the galaxy actually looks different. And in terms of models of formation, it's a big constraint for theoretical models, because you have to know that, the density in the high redshift universe is very high. So you have a lot of collisions going on and, creating those irregular galaxies. And the fact that there are so many disk galaxies at this time already means that they basically haven't experienced a collision in a while, right? So they have to be somewhere isolated. And that's something we have to understand now.
We had another question back here. I assume you were done with your answer. Okay.
Yeah.
Here you go.
Thank you for an excellent presentation. I had a question about dark matter halos. So what is the structure in terms of distribution of dark matter in a halo? And then how does that change? What's the natural history over time, over long periods of time, in terms of how that evolves and then how that affects galaxy formation?
Very good question. So you can think of it as it's very peaked, basically, and then almost like an exponential fall off. That's how it looks like if you do a cut through the halo. Well, how do we know that? That's a different question, but you can measure it with weak lensing, for example. If you want to know, I have some slides on that too. And now how does it change over time? Well, actually, yeah, let me just show a slide here. It depends on the it's basically, if you just have a galaxy in isolation, you can think of it as this like exponential fall off in 3 dimensions, right? But if you have a galaxy merger, so 2 galaxies collide, what you then see is more like an elongated dark matter structure. So you can use, if you measure the dark matter and the dark matter substructure of galaxies, you can also say something about the what the galaxy experienced in the past years, well, million years or billion years even. And so, for example, here, so these are to actually show this, you have to go a little bit to bigger scales here, and so these are now showing 2 galaxy clusters, right? So it's basically like the SMACs, but 2 of them together. And so see all the galaxies here are the points, and then the green contours is the dark matter distribution. And so you see here, it's kind of circular, spherical, right, around each of the clusters. But then you have those bridges basically in between, which tells you that those 2 galaxy clusters are merging, right? And you can think of it for single galaxies the same way, right? If you have single galaxies merging, the dark matter halo is kind of combining, and if you can measure that, you know how those are merging. And the thing is, because dark matter is collisionless, it's super easy to simulate that, right? So there's a relaxation timescale that dark matter needs from like this kind of configuration to go back to a compact configuration, which is a couple billion years. And so you can get timescales from that, how long it takes for those 2 galaxies or for 2 clusters to merge.
Got any more questions? Oh, here's a couple in the front here. Hang on. What would you like to do first?
Excellent presentation. Thank you for taking the time to share your knowledge with us. I do have one question on artificial intelligence and machine learning and how it's enabled you to make analyses into your analysis of the James Webb data. Has it made it easier? Have you been able to amplify your scientific processes and your discoveries?
Yes, indeed. So, so the problem we have, right? We start to have a lot of data, right? And so the work I showed you here with those disk galaxies versus spheroids, and these are 100,000s of galaxies to look at. And obviously we didn't have a student to do this for like 2 weeks, just looking at galaxies and classifying them. And so here's where AI and machine learning comes in. And we do have, I would say it probably picked up it very recently. So in the past, maybe 3, maybe 4 years max, it picked up a lot that you see more and more people using it on large data sets, mostly to classify galaxies, like into spheroids and disk galaxies. And so we use this for this analysis actually, and with basically with a neural network. And that basically, yeah, I mean, without that, it will not be possible to do this analysis anymore with the JWST data. Yeah, it's more, it's kind of you get you can get better statistics, right? And it's kind of not depending on people itself, right? Although we still have so machine learning is always a little bit of black box, right? So it basically what you put in kind of comes out, right? And so what we're still doing, we do citizen science projects, and maybe you've heard of Zooniverse, and we are actually setting one up for our Cosmos Web observations, where people can go and look at those images and classify them, and also at the same time learn something, right? Is it this galaxy? Is it a merger? This is a gravitational lens here, right? So it's both machine learning and visual classification is still important. But yeah, in terms of speed and everything is not comparable to like 5 years ago or 6 years ago.
Okay, I'm going to also look at our chat here and see if we had any questions come up in the chat. So hang on. Okay. Well, okay, no, not that one. Are the early cluster similar to the globular cluster around our galaxy now?
Yes, very good question. So they are generally more metal poor than today's cluster, and that basically depends on the environment where they're being formed, right? So if they are formed in an early galaxy where there is generally less metal, right? So the stars are basically less metal enriched. So the star clusters are also less metal enriched in those. In terms of age, they are usually younger, right? Because they're just being formed earlier. An interesting question we haven't solved yet is when they're actually forming. So it seems like they might form at a very similar time in the timeline. And then just some of them we see now earlier, and then the other that we see today. But then there are some publications that claim to find globular clusters in very early galaxies, so redshift 7, 8. And they are usually, by a selection effect, they're usually bright, right? Because they're so far away. And so they're supermassive. And so we actually don't know if they are globular clusters, I mean star clusters, or if they are dwarf galaxies that are orbiting those early galaxies. But yeah, so generally to answer your question is they are more metal poor and usually younger than what we see today.
Okay. So there's a two-parter here. It says how many stars in the Milky Way and how many in the largest of galaxies?
Okay. So Milky Way has around 100 billion stars.
Mm-hmm.
And the Milky Way is kind of on the massive side. So you might be able to get a factor of 5 or 6 more in the most massive galaxies today, which are the ones I show you here. So these elliptical galaxies here. So they maybe have close to, maybe 500, 600 billion stars, sorry.
Mm-hmm.
Mm-hmm.
So I guess one thing to ask would be compared to current sized galaxies, are the early ones big or small in general?
In general, smaller. Yes.
Yeah.
So our Milky Way is about 100,000 light years across, right?
Mhm.
So the first galaxies I showed you here, they are about maybe 10,000, like a factor of 10 smaller.
Good. Okay.
Mhm.
All right. The last question on the chat at the moment is, are the furthest galaxies moving away from us faster than the speed of light? And if so, could we ever see them? Well, I'll let you answer that one.
Yeah, so that's a good one. So you can, so if they're flying away, then more than speed of light, you cannot see them, right? Because the light cannot catch up.
Right.
Yeah.
Yeah, well, things usually don't move faster than the speed of light.
Yeah, unless the space in between is also moving and kind of funny stuff happens. Yes.
Yeah, right. Well, one of the classic examples or explanations, if you have two spaceships headed toward each other at 99% of the speed of light, and you shine a flashlight ahead of each spacecraft, the light doesn't go any faster, right? So anyway, any more questions here tonight? Oh, got one on the back. Hang on just a second. I'll get back to you. There you go. Ask away.
Please forgive me. I wasn't able to see part of your presentation, so you may have touched on this, but what I've heard about the recent observations of the James Webb telescope of the deep field views are that there's something like 1,000 to 10,000 times the number of galaxies that we thought should be there. And I think Hubble had found this too. And the way I understood it is I'm not trying to contradict you, but what I heard is that the galaxies appeared small in the Hubble deep field, and in the James Webb, they're large and well formed. Some of the galaxies are 10 times the diameter. Some of these spiral galaxies are 10 times the diameter of our current galaxy. I mean, the Milky Way. And I'm wondering if you've heard about this, if I have this right, and wondering what you think.
Yes. So I think the galaxies you're thinking about are those diffuse ultra large galaxies, right? So they are much bigger than our Milky Way. And so they have been found, and they can be quite big, and they have like a very low surface brightness appearance. And so they are usually they're usually around overdense regions like galaxy clusters. Is that what you mean? Those?
Yeah. You're talking about,
Yeah, I'd heard this. I don't know if it's true. It must be true. It was on YouTube. Anyway,
Oh yeah, these are.
but they're 10,000 times the number of galaxies that we predicted. And the way I understood, as far as it was implied that with the Hubble observations that there's small proto-galaxies probably collided and formed the number of galaxies we have now. But like I said, we're seeing all these fully developed galaxies in the early universe. And I don't know anything about it. That's why I'm asking you, because I've heard this and I haven't heard much about it. It seems awesome. Anyway, that's what I've heard.
Yes, yeah, and this is why we were surprised, right, to see those pretty evolved galaxies already, right? And then obviously with JWST, you can also go much fainter. And so at some point, I mean, how small is the smallest galaxy, for example, right? I mean, we don't know that. We are seeing galaxies that are smaller and smaller and fainter now with JWST, and there are basically two models, right? Either they get basically killed by feedback, right? So if you have a very small low mass galaxy and a supernova goes off, it basically just blows out all the stars, right? Because you have a low gravitational potential in this low mass galaxy, or it can be kind of kept together, right? And so there were also some of those very faint galaxies being found, and so we basically have to adjust our theoretical models a little bit.
Yep, that's what we always do.
Yeah,
At least you guys do. There's another question here on the chat. There is a recent report on phys.org that supermassive black holes are a likely source of dark energy. I have seen others who are skeptical. Have you seen this?
yes, yeah, and I'm also skeptical. It's trying to, so yeah, I mean, it's trying to basically explain something, right, with in a different way, right, which is good. But they are basically what we found when we looked at this publication is that they are probably easier ways than dark energy mathematically to explain the supermassive black holes.
And I don't think they've really made a connection, at least not a proper one, between dark energy and dark matter.
Yes.
So, yeah. So one has to wonder. Any other questions here? Oh, got another one. All right.
Does any of your work looking at galaxies over such a long period of time, can you comment on the current state of the Hubble tension, and if any of your work can shed light on that?
So not directly my work, but what you see here, let me see. Oops. Uh-oh. No. So basically with with all this, so basically how you can measure that is by one way to measure the Hubble constant is by looking at the time delay of lensed sources, right? So you basically have a variable source, and then you have a cluster or a massive galaxy, and you basically lens it. And so it's stretched it out like you see here in this image. And so, and now you can measure basically the time delay, how long of this flashing background galaxy, this variable source, how long it takes for the different lensed images of this galaxy to appear. And so that's how people basically measure that. And with JWST, you can go much fainter, right? And you have high resolution. So I expect that there will be a lot of those observations being done, right, where you can actually measure the Hubble constant much better than we know now, right, and hopefully resolve the tension. So again, yes, sensitivity and resolution helps you in that way.
Got another question for you here. Hang on.
Since the launching of the JWST, we've seen an awful lot of images in the media attributed to it, but many of them contain colors well outside of the infrared spectrum. How are they augmented?
Yeah, that's a good question. So, but let's stay with this image here, right? So the red things you see here on this image, you couldn't see them by eye, right? Because they're far beyond our capabilities. So basically what they do when they make these images, they basically assign each image. Where is it? Yeah, right. So you basically from the telescope, you get an image in I don't know, 6, 7, 8 different filters. So you basically bunch them together and you just assign them an RGB and put them together. And that's how those images are being made. But you're right. I mean, you can't see. I mean, this is 0.9 micrometers, so 900 nanometers. That's basically already where our vision is we can't see this anymore. So everything you see here on those images, it's all in the infrared. You can't see it by eye in the visual. And yeah, and there's a lot of tweaking to adjust their color. It's kind of like an art, right? To make those kind of images.
Yeah,
So
it's kind of a convergence between art and science, if you will.
exactly, yeah. And we actually, so they have at NASA and also Space Telescope Science Institute, they do have people that do this for their life, right? So they give them images and they do this nice composites that we see here. Same with this one, right? I mean, this is it's just beautiful.
Well, for instance, even in the Hubble images that we have seen for decades or more, are all color shifted in one way or another. So, and this is just an exaggeration of that.
Yeah.
Factor 10, I think. Okay, anybody else have a question? Oh, yes, there's one here. Sorry, I forgot.
So this might not have to deal with James Webb Telescope information, but do you personally have an idea or a theory of maybe like throughout the life cycle of a galaxy when it would have the highest potential for, let's say, life to be developing in there? Like, is it an older galaxy that would have more life, or a younger one, or one that's middle-aged, or do you have a hypothesis?
Yeah, that's a good question. So, but we see, so just from like probability, right? So you see life around older stars, like what we see, I mean, where we look currently for exoplanets and maybe also life is around the older stars, like M stars, right? The cooler ones. And so in order to form those stars, you already have to have the galaxy already have to exist for a couple billion years. And so, well, if you look in the timeline, right here, here, right? So if you look here, in order to form those stars, you probably have to live like the galaxy has to be exist for like 2 or 3 billion years. So maybe you can probably start forming those planets or have those kind of planets around the redshift 2 maybe, and then you still have 10 billion years to develop life basically, right? Or and planets, right? Yeah, it's a great question. And I would also say, I mean, when you go at very high redshift, right, the environment is much more harsh, right? You have more of this ionizing radiation from those young hot stars, right? They eventually, they cool off, and the most massive stars, they explode, right? And then the lower mass stars, they live for a longer time. Yeah, excellent question. My guess is, it can happen quite early in the lifetime of galaxies.
Okay, we got one more question on the chat here, which is, let me try to condense it a little bit. Is there always an association of galaxies with their dark matter?
In general, yes. There have been, so in general, yes, there is. There have been, you can measure galaxies in single dark matter in single galaxies by measuring the speed of the globular cluster in that galaxy. How they circle around the galaxy, and from that you can measure a total mass. Right? It's basically kind of the more massive the faster it spins, basically. And so it has been found for some galaxies that they have a lower abundance of dark matter. And those are actually the galaxies that I mentioned before, those ultra diffuse extended galaxies. So they can have a lower amount of dark matter. So there is a bit of variation, yes, but no dark matter, I have not seen anything. Yeah, that will be quite interesting though, because to form a galaxy, as I said in the beginning, you have those dark matter clumps, right, where the gas is flowing in, attracts the gas, and then it forms stars. So if you don't have dark matter in a galaxy, that will be very interesting, and how you would form or assemble the galaxy actually.
Right. We're kind of running a little long here, so I think I'm going to have to close out questions. But anyway, thank you very much, Dr.
Yeah.
Faisst.
Thank you.
Thank you.
And
Thank you.
I think everybody enjoyed it.
yeah, thanks for having me. And if you have questions, you're welcome to reach out to me anytime.
Thank you very much. And good night, all.
Good night. Thank you.
Bye-bye.
Bye.
Let's see where we can. Can't find it. Oh, there it is.
Nice.